All right, so let's talk about 6.9, which is about hyperbolic functions and hanging cables. I think they throw the hanging cables in there just to make it seem like it's an application section. Truthfully, it's not an application section. This section is all about hyperbolic functions. So it's kind of interesting because chapter 6 is, the title of the chapter is Applications of the Definite Integral in Geometry, Science, and Engineering. And we have talked about a lot of applications of the definite integral. We've talked about the area between curves. We've talked about the volumes of surfaces of revolution. We've talked about the length and surface area of the length of a curve and the surface area of a surface of revolution. We've talked about work. We've talked about centers of gravity. We've talked about fluid pressure and force, right? All of these things are applications of the definite integral, and of course there are more. You probably saw in Calculus 1 some applications of the definite integral when it came to position, velocity, and acceleration, right? But anyway, and of course there are others as well. But the last section in this chapter is it's really about hyperbolic functions. And there are, of course, applications of hyperbolic functions, but that's really not the main point of the section. The main point of the section is to introduce these new functions to you, and they're really kind of cool. So let's get into it. Okay. So hyperbolic functions, you'll notice that they've got similar names to the trigonometric functions, and there are reasons for that we'll talk about here in a second. Okay, and then the way that we say these is so this is the hyperbolic sine function, but for short we'll call it cinch, right? So cinch of x is defined to be e to the x minus e to the negative x over 2. Similarly, this is the hyperbolic cosine, but we'll call it cosh or cosh. I might go back and forth, but anyway, cosh of x is e to the x plus e to the negative x over 2. This one we'll call, well, it's hyperbolic tangent, but we'll call it tanh of x. And we define the tanh of x to be the cinch of x over the cosh of x. Or if you make those replacements, you see that it's e to the x minus e to the negative x over e to the x plus e to the negative x, right? And similarly, we can define cosecant, right, to be the reciprocal of the cinch function, right? Just like cosecant is the reciprocal of the sine function. We can define sech to be the reciprocal of cosh, and cotanh to be the reciprocal of tanh, right? Anyway, they just make me chuckle, these names. I'm not the one who came up with the names, by the way. But anyway, let's practice with this a little bit. So let's calculate cinch of 0, cosh of 0, and then cinch of 2. Okay, cinch of 0. Well, by definition, cinch is e to the x minus e to the negative x over 2. Well, anything to the 0 power is just 1, except for 0 itself. That's an ambiguous case, right? Negative 0 is just 0. So this is just 1 minus 1 over 2, which is 0. Okay? Cosh of 0 is e to the 0 plus e to the negative 0 over 2. That would be 1 plus 1 over 2, which would be 1. And cinch of 2 would be e squared minus e to the negative 2 over 2. That's about as clean as you're going to get that. I mean, I suppose you could multiply top and bottom by e squared to clear the negative exponent there, and you get e to the 4th minus 1 over 2e squared, right? That's an equivalent form for it. And I suppose you could also do some kind of like difference of squares thing, right? If you're thinking, you could think this is e minus e to the negative 1 times e plus e to the negative 1 over 2. I don't know. There's a whole bunch of ways to think about it. In this case, I was jumping from here to there. If you thought of this as a difference of squares, well, that would be e squared plus 1 times e squared minus 1, right? Anyway, whole bunch of different ways to get it. But if you want a decimal approximation, obviously you're just going to have to punch that into your calculator. So e squared minus e to the negative 2 over 2. Look at my facetious little calculator. It says, oh, that's just the cinch of 2. Of course it is. But it's about 3.6. Okay, so that's that. All right. So the next thing that that kind of comes up in this section is that there are all kinds of identities that are true for these hyperbolic functions that really kind of mirror a lot of what you see with trig functions. Okay, so I just listed 3 of them here, but if you look at this theorem in your book, and by the way, this theorem is on page 401. So this theorem 6.9.2, is on page 401, and it lists 14 identities. Now, you could put those on flashcards and try to commit them all to memory. Honestly, I wouldn't really do that, but actually let me pull them up. So 6, and oh no, I need it from Math 65 because I've got the textbook. Okay. Okay, sorry, my book was taking a while to load, but anyway, here it is. So here's that theorem, 6.9.2. So you'll see, you've got all kinds of nice things. Now, we'll talk about these first couple, but notice, if you're dealing with just a straight up trig function, we know that sine squared plus cosine squared is 1. Well, if you're dealing with the hyperbolic function, what you get is cosh squared minus sinh squared is 1, right? And similarly, you have like these other kind of Pythagorean identities that sort of match, but not quite the Pythagorean identities that you knew for the trig functions, right? You also have even odd identities, right? So cosh is an even function just like cosine is even. Sinh is an odd function just like sine is odd. You have these sum and difference identities. You have these double angle identities, right? So sinh of 2x is 2 sinh x cosh x, just like sine 2x is 2 sine x cosine x, right? So lots of similarities between the hyperbolic functions and the trig functions, and we'll talk about why that is here in a second. But for now, let's prove just a couple of these. And again, I'm not going to go over all of them, but looking at the first one, right? Cosh x plus sinh x equals e to the x. Well, that just follows straight from the definition, right? Because cosh x is e to the x plus e to the negative x over 2. Sinh x is e to the x minus e to the negative x over 2. And so if you combine like terms, you get e to the x plus e to the x is 2e to the x. E to the negative x minus e to the negative x cancel off, so you just get 2e to the x over 2, and that's just e to the x, right? Or like the third identity, cosh squared minus sinh squared equals 1. This is pretty easy to prove, right? Cosh squared minus sinh squared is e to the x plus e to the next, cosh squared is e to the x plus e to the negative x over 2 squared. Sinh squared is e to the x minus e to the negative x over 2 squared. When you square those, we'll get e to the x times e to the x is e to the 2x. E to the x times e to the negative x is 1. You'll have 2 of those, so it'll be 2. And then e to the negative x times e to the negative x is e to the negative 2x. And then 2 squared is 4. And similarly, when you expand this one, this is what you get. And then when you combine like terms, the e to the 2x's cancel. The e to the negative 2x's cancel. You have a 2 minus a negative 2. That makes a 4, right? 4 over 4 is 1. And that proves that one, right? So you can kind of go through the rest of those, you know, if you're interested. You could go through and kind of prove them all just by making that kind of replacement. Okay? So let's talk about why these things are called hyperbolic functions. So it helps for us to think about trig functions as circular functions. So you may have learned back from your trig days that the trig functions, the trigonometric functions, are also known as circular functions. And the reason that we call them circular functions is because if you take an ordered pair, cosine t, sine t, then that ordered pair is a point on the unit circle, x squared plus y squared equals 1. And this is something that, again, you would have learned in detail from trig, right? So trig functions are known as circular functions because of this fact, right? Well, in a similar way, if you take a point cosh t, cinch t, it turns out that that describes a point on the unit hyperbola, x squared minus y squared equals 1. And that's easy to prove, right? Because if you look at x squared minus y squared, if x is cosh t, then x squared is cosh squared. If y is cinch t, then y squared is cinch squared, right? And we just proved that cosh squared minus cinch squared is 1, right? We just proved that up here, right? So we know that cosh t cinch t has to be on this hyperbola. And that's why these things are called hyperbolic functions. So they're called hyperbolic functions because cosh t cinch t describes a point on the unit hyperbola. We give them similar forms to the trig functions because they have so many nice properties that are so similar to like the trig identities, right? Anyway, so that's kind of a basic introduction to these hyperbolic functions. There's more information, and I would encourage you to at least glance through the pages in the textbook for this section, because they'll give you the graphs of these things, so that you know what they look like, and just give you a little bit more information about all this stuff. But I don't think it's too helpful for me to just sit here and read a textbook to you. So I'm not going to go through all of that. But they talk about the graphs, they talk about the domains and ranges and all of that stuff, right? So it's good information. I would look through it if I were you. It might come in handy later on. One thing that you'll notice if you look at the graphs of all of the hyperbolic functions is that most of them are one-to-one. The ones that are not one-to-one can be made to one-to-one by restricting their domains to a certain degree. And so consequently, we can talk about inverses, right? They're going to pass the horizontal line test, so they're going to have inverses. And because the hyperbolic functions are describable in terms of the exponential, right, e to the x, it's not surprising that the inverse hyperbolic functions are going to be logarithms, right? They're going to be logarithms. So in particular, these are the formulas, and this is theorem 6.9.4 from the textbook. But the inverse of the hyperbolic sine is the natural log of x plus the square root of x squared plus 1. And the inverse of the hyperbolic cosine, right? So cosh inverse, cinch inverse, cosh inverse is natural log of x plus the square root of x squared minus 1, right? And similarly for the rest of them, right? I'll prove the first one to you. Okay, so to prove it, we do the same thing that we usually do when we're trying to find inverses. That is, we swap x and y, and then we try to solve for y, right? So if I say x equals cinch y, well, cinch y is just e to the y minus e to the negative y over 2. Now I can multiply both sides of this equation by 2 to get 2x equals e to the y minus e to the negative y. And then I can also move this 2x over to the other side. So then I get e to the y minus 2x minus e to the negative y equals 0. And then finally, I can multiply this equation through by e to the y power. And if I do that, I get e to the 2y minus 2x times e to the y minus 1 equals 0. And now here's the tricky part, right? Here's the cool part. If you squint at this just right, you'll notice that this is a quadratic in e to the y. In other words, e to the 2y is the same thing as saying e to the y quantity squared, right? So here you have e to the y squared minus something times e to the y to the first power minus a constant. Well, so that's just a quadratic. It's a quadratic in e to the y. So we can solve that by saying, all right, by using the quadratic formula, we can say, okay, so then e to the y equals negative b, so negative 2x is 2x, plus or minus the square root of b squared, that's negative 2x quantity squared is 4x squared, minus 4 times 1 times negative 1. Right, that's going to be a plus 4. All divided by 2 times 1, so 2. Now, here we can factor out a 4 and take the square root of 4, and it would be 2. And we can take that out of the square root, and then we can cancel all the 2's. And the result would be that we would get x plus or minus the square root of x squared plus 1. Okay, finally, we're almost there now, right? So e to the y equals either x plus root x squared plus 1 or x minus root x squared plus 1. Well, notice that an exponential always has to be positive. And also notice that x squared plus 1 is always going to be bigger than x. Or I'm sorry. Let me say that differently, right? The square root of x squared is sometimes equal to x. Sometimes it's equal to it's equal to the absolute value of x. We'll say it that way, right? So the square root of x squared plus 1 is always going to be slightly bigger than square root of x squared, which means it's always going to be slightly bigger than x. So if I have x and then I subtract something slightly bigger than it, I get a negative number. And that can't happen because e to the y has to be positive. And that means we must take the positive version, right? It must be x plus square root of x squared plus 1. So e to the y is x plus square root of x squared plus 1. Finally, to finish solving for y, we take natural log of both sides and we end up with the result that was stated in the theorem. Okay? So it's interesting, right? These hyperbolic functions, the inverse of the hyperbolic functions all have these logarithmic forms. Okay? Which is really nice. Okay? So let's do a couple examples. Let's calculate sinh inverse of 1 and tangent inverse of 1/2. So sinh inverse of 1. Well, we know that sinh inverse of x is equal to natural log of x plus the square root of x squared plus 1. So in this case, that would be ln of 1 plus the square root of 2. And that's as good as that one's going to get. You're not going to get it, algebraically, you're not going to get it looking nicer than that. We can give a decimal approximation. So we can say this is a natural log of 1 plus square root of 2. That's about 0.88. Okay, and then similarly, right, we can do tangent inverse of 1/2. I don't know why I put parentheses around that. You don't need it, but anyway. Tangent inverse of 1/2. So we know that tangent inverse of x, according to the previous theorem, tangent inverse of x is 1/2 times the natural log of 1 plus x over 1 minus x. Okay, so that's 1/2 times the natural log of 1 plus 1/2 is 3/2. 1 minus 1/2 is 1/2. That's 1/2 times the natural log of 3/2 times 2 would be 3. And again, that's about as good as you're going to get that. I guess you could call it natural log of the square root of 3 if you want. But anyway, 1/2 natural log 3 is 0.55 approximately. Okay. All right, so that's that second example. So far all I've really done is just introduced the hyperbolic functions to you and then the inverse hyperbolic functions to you. Again, we haven't looked at things like domains and ranges or graphs or anything like that. We didn't look in a ton of detail at all of the various identities and stuff. That would all be useful information for you to kind of look at. What I do want to talk about in maybe a little bit more depth is the derivatives and integrals of these hyperbolic functions. So this is theorem 6.9.3 from the textbook, right? And again, you'll see how nicely this corresponds to the trig functions, right? So the derivative of sine is cosine, and so similarly, derivative of sinh is cosh, right? Derivative of cosine is negative sine. Well, derivative of cosh is just positive sinh. All right, so that's a little bit different, but still similar, right? And by the way, if the derivative of sinh is cosh, then that means the integral of cosh is sinh. And similarly, if the derivative of cosh is sinh, then the integral of sinh is cosh, right? Derivative of tanh is sech squared, so the integral of sech squared is tanh, right? And so forth, right? But again, if you look this up in your textbook, 6.9.3, theorem 6.9.3, it gives you all of the derivatives of all of these hyperbolic functions. So again, this is going to be a useful page for you to look at. These you definitely should make flashcards of and commit to memory, right? So you should commit this theorem to memory for sure. Okay. Let me prove this to you. So I'm just going to prove this first one. And the rest of them, the proofs of the rest of them are similar, right? But let me just prove this to you real quick. So proof of the first one. Derivative of sinh x. Well, sinh x is just e to the x minus e to the negative x over 2, right? And the derivative of that, well, we could pull out the 1/2, I suppose, and then you just take derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times negative 1, and that's going to make this negative a positive, right? So derivative of e to the x minus e to the negative x over 2 is just e to the x plus e to the negative x over 2. Well, that's just cosh, right? So that's all there is to that. Okay. So let's see an example. We'll work out several examples of some things. So we want to calculate the derivative of cosh of x cubed. Okay, so the derivative of cosh x cubed. We're going to use chain rule here, right? So the derivative of cosh, first of all, is sinh. But then we have to do the derivative of that inner function. Derivative of x cubed is 3x squared, right? So it's going to be 3x squared sinh x cubed. Okay, that's that. What about derivative of ln of tanh x? Okay, again, chain rule, right? So we'll say, well, the derivative of a natural log is 1 over whatever the argument is. So it's, in this case, 1 over tanh x. But then times the derivative of the argument. So we have to multiply by the derivative of tanh x. So derivative of tanh x is sech squared, right? Sech squared x. It's too bad they didn't do, I say they because I copied this from your textbook, but it's too bad we didn't do something like natural log of tanh of, x squared plus 4 over x cubed minus 3 or something, and then we could have done like a chain rule within a chain rule type of thing. But this is actually kind of nice, come to think of it, because I'm sure that there are some trig identities we can use here, or not trig identities, but hyperbolic identities rather, because 1 over tanh is cotanh, And in fact, we can call this 1 over sinh over cosh, or in other words, cosh over sinh. So I'm going to call this cosh x over sinh x. And then sech squared is 1 over cosh squared, right? So the reciprocal identities and stuff, they're just like the trig functions, right? They're just like the trig functions, so, which makes it nice. Because now this will cancel one of those. I get 1 over sinh x cosh x, which, by the way, you could write that differently, I suppose. We know that 2 sinh x cosh x is sinh 2x. So I could put a 2 here as long as I offset it with a 2 up there. And then I could call this 2 over sinh 2x, right? So I could say this is also 2 over sinh 2x, right? Which, you know, depending on your preference, maybe you like this better, maybe you like this better. It doesn't really matter. It's the same thing. Okay? Or I guess you could have even left it as sech squared x over tang x, right? Right? I mean, that's also, you know, fine. Okay. Well, let's do another one. Let's do an integral. So let's integrate sinh to the 5th x cosh x dx. Okay. All right. I think I'm going to do a u substitution. I'm going to let u be sinh x, because if I do that, then du is going to be derivative of sinh is cosh, right? It's going to be cosh x dx, and look, this is du. So there's du. And sinh we called u, so this is just u to the 5th now. So it looks like we've got, so we'll say and integral sinh to the 5th x cosh x dx is going to now become integral of u to the 5th du, right? By making that substitution. And that's easy, right? This is going to be u to the 6th over 6 plus c. Or if we want to convert it back into x's, then we would say this is sinh to the 6th x over 6 plus c. And that's that one. Let's do another integral. So let's do integral of tang x dx. At first glance, this might seem kind of simple, except that you'd have to find a function whose derivative is tang, and you're not going to find one, right? So in order to find the antiderivative of tang, we might have to be a little bit more clever. But it's not too challenging. Notice that tang is sinh over cosh, and the derivative of cosh happens to be sinh. It's sitting right up there, so we'll do a u substitution, right? By the way, if you thought your days doing u substitutions were over, guess again. You're going to be doing lots of those. So let u be cosh x, then du is derivative of cosh is sinh x dx. So then this stuff is du, and this is just u. So integral of tang x dx turns out to just be integral of du over u. And that's natural log of absolute value of u plus c. Then back substituting in for x, we get natural log of cosh x plus c. Okay. And that's that. Okay. So, all right. So we've talked about hyperbolic functions. We've talked about inverse hyperbolic functions. We've talked about derivatives and integrals of hyperbolic functions. Now, let's talk about derivatives and integrals of inverse hyperbolic functions. Okay, and your book splits this up into two separate theorems, Theorem 6.9.5 and Theorem 6.9.6. Let me just show them to you. 6.9.5 is all about the derivatives. 6.9.6 is all about the integrals. So again, make sure that you look at those in the book. But here are the first few. Okay. So the derivative of Cinch inverse is 1 over square root of 1 plus x squared. And so that means if you want to integrate something of the form 1 over square root of a squared plus x squared, then that's going to be a Cinch inverse type of thing. In particular, it's Cinch inverse of x over a. Okay? And then we've got similar statements for cosh inverse and tangent inverse. And as well as for the other three hyperbolic functions. As you saw a second ago when I pulled up the textbook, you may note that the integrals here, they each have their logarithmic form, right? So remember that cosh inverse of whatever is the natural log of x plus the square root of x squared plus 1, minus 1. Minus 1, x squared minus 1. So so you could also rewrite this as ln of ln of x over a plus the square root of x squared over a squared minus 1, right? Or I guess I've already written one down for Cinch, right? So integral of 1 over square root of a squared plus x squared is Cinch inverse of x over a plus c. But that's equivalent to the natural log of x plus the square root of x squared plus a squared plus c, right? Anyway, but let me just prove this first derivative to you so you see kind of where these things are coming from. Okay, so the derivative of Cinch inverse, if I use the logarithmic form, Cinch inverse is natural log of x plus square root of x squared plus 1. And the derivative of that is going to be 1 over x plus square root of x squared plus 1 times the derivative of x plus square root of x squared plus 1. Well, that derivative is going to be 1 plus, if I think of this as x squared plus 1 to the 1/2, it's going to be 1/2 times x squared plus 1 to the negative 1/2 times the derivative of the inside, x squared plus 1, which is just 2x. Okay? We can simplify that a little. The 2 will cancel the 1/2, right? This x squared plus 1 to the negative 1/2 becomes a square root of x squared plus 1 in the denominator. This x ends up in the numerator. Finally, if we combine like terms here, we can call this square root of x squared plus 1 over square root of x squared plus 1. And then when we add them, of course, we're going to get square root of x squared plus 1 plus x all over square root of x squared plus 1. When we multiply that by that, we get square root of x squared plus 1 plus x over x plus square root of x squared plus 1 times square root of x squared plus 1. And then notice that this term cancels that one, and we end up with 1 over square root of x squared plus 1, just like the formula said we should. Okay. So let me give you an example of this one. So let's calculate the integral of dx over square root of 4x. My pen out of ink. My pen might be out of ink. Hold on a sec. Dx over the square root of 4x squared minus 9 for x greater than 3/2. That requirement is only there to make sure that that our integrand is positive, right? Because you can't take the square root of our radicand, and that's because you can't take the square root of a negative number, or you can, but it's just not a real number. And this is a course in calculus, so we're dealing with the reals. To see how calculus works with complex numbers, you have to take a course called complex analysis. Anyway, so let's see if we can do this. So the trick here is to realize that you've got to get this in the form where you've got something squared. And for 4x squared, so for 4x squared, that something is actually 2x, right? So this is kind of the format, right? It's a 2x quantity squared minus a 3 squared. So I want this to just be a single variable, so I'm going to do a u substitution. Let u be 2x. Then du is going to be 2 dx. I can force a 2 dx up here as long as I offset it with a 1/2 there. Okay, and doing that's nice because now I've got du and I've got u squared minus 3 squared. So now I've got this situation. I've got 1/2 times the integral of du over the square root of u squared plus 3 squared. Okay, and then according to the previous theorem that we just looked at, this is a cosh inverse format, right? This is cosh inverse of u over 3. So this is 1/2 cosh inverse of u over 3 plus c. And then I can replace u with x. And so I get 1/2 cosh, not cosine inverse, cosh inverse of 2x over 3 plus c. And that'll do it, right? And that's that one. Okay. So those are the hyperbolic functions. Now, again, the name of this section is Hyperbolic Functions and Hanging Cables. So let's talk about why hanging cables. Well, it's hanging cables because it turns out that whenever you've got homogeneous, that means like same density, same thickness, whatever. When you've got a homogeneous flexible cable that you suspend between 2 points, like say telephone poles, right? And telephone wires hung between 2 telephone poles, the cable forms a curve that we call a catenary, and the catenary has an equation of the form y equals a cosh x over a plus c. So it's a hyperbolic function. A and c are determined by the distance between the poles and the composition of the cables, right? What they're made out of and that kind of thing, their thickness and so forth. What else did I want to say about that? Well, so in the textbook, they go through a couple examples where they do things like, you know, a wire is stretched between two telephone poles, and, you know, calculate the length of the wire or whatever. In order to do that, at some point you have to use like some kind of software to solve an equation for you, because we don't have really a good algebraic way to solve that particular equation. And so I would just rather not give that example. So the only reason I mention this is just to explain why the title of the section is about. It includes information about hanging cables, but also just to give you an application for why we might be interested in hyperbolic functions. And it's because, you know, they do come up in nature. Of course, hanging cables isn't the only place that hyperbolic functions come up, but it is one example. So anyway, that's, I think, all I'm going to say for 6.9.